Hello everyone. In today's lesson, we are going to simulate MDA based CO2 capture process in Aspen Plus V14. This is the process flow diagram, and here we want to remove CO2 from this feed gas. This feed gas mostly contain hydrogen, some carbon dioxide, and some traces of CH4 into CO and H2O. Carbon dioxide is removed from this gas using MDA solvent. So the solvent contains 50% MDA and 50% H2O. At the top, we get our clean product, which is mostly hydrogen, and here we get the rich solvent, which has the captured CO2. So this rich solvent is heated and then it is sent to a stripper where this solvent is regenerated. The stripper is actually a distillation column. The number of stages and other specifications are given here. So in the bottom, we recover our solvent, and this solvent is recycled and again fed to the absorption tower. And the top product, this mostly contains the gases, carbon monoxide, carbon dioxide, CH4, carbon monoxide, nitrogen, and some traces of H2O. So this this product stream is cooled and it is passed to a fresh drum, and the water is recovered from this stream, and the gaseous stream mostly contain the captured carbon dioxide. So this water is also recycled to the absorption tower. Here we add some makeup solvent because in this stream, in the hydrogen stream, some solvent may be lost here and some solvent may be lost here. So to compensate those losses, we add the makeup solvent here. So in the first part of this simulation, we will do the once through simulation. By once through simulation, I mean that I will not be recycling these regenerated solvent, this one and this one. In the second part, we will close the loop, and we will recycle the stream and that regenerated solvent, and that will be fed into the absorption tower. Okay, now open Aspen Plus. I am doing this in Aspen Plus V14. If you have an earlier or a later version installed, you can do the simulation in those versions as well. Because normally the changes, those are very advanced, and the steps of the simulation are almost similar. Now click on New and select metric units, electrolytes with metric units. So you can see that it tells you that these units will be used, and this will be the property method that will be used. This is the flow basis, and the stream report composition. This will be in term of the mass flow. Now click on Open Selected. So when it opens, you can see that H2O is added by default because we have selected electrolyte template, and you can also see that in the methods, elect inertial is added by default. Now I will import the data package which is already available, which is provided by the Aspen. So when you install the Aspen, this is already copied in your computer. So click on File and click on Import. Click on File and go to C, Program Files, and then Aspen Tech. Okay, and now Aspen Plus V14. Aspen Plus V14. So if you have earlier version, you should open, like if you are using Aspen Plus V11, you should have the folder, you should have the relevant folder. So I will open Aspen Plus V14, click on GUI, data package, and now KEMDEA, select this. So these are some of the parameters that tells you that what is there in this package. These are the components. This is the property method that will be used. So just double click on KE MDEA. Okay, and provide the names here for the components. This is H2O. I will just call this MDEA. You can also enter any other name. This is H2S, and I will call this as CO2. Click OK. Now, if it is asking you that these things already exist, because you saw that we have H2O here, and we also have this electrolyte NRT emitter. So it is asking you, do you want to replace, do you want to merge this, or do you want to ignore? So select both. Just click on replace or click on ignore. This will do the same thing. And click OK. So you can see that these components have now been added. The MDA, H2S, carbon dioxide, and their ions. And you can also see here in the chemistry that these are the reaction data have been added here. The specification of the reaction, other things you can see it here. All of the reactions that have been added. So just click run to ensure that everything works properly. And now in our problem, we also have some other components which are not added here. That is H2, hydrogen. Just click on yes, and carbon dioxide. Sorry, carbon dioxide already exists. Carbon CH4, methane, carbon mono, and N2. And now just click on next. It is actually asking you to confirm this parameter, so just click next, and now click run. Now go to the simulation. Okay, in properties, actually this is always recommended to have all of the components at the top and the ions in the bottom. So I will just reorder them. So select this with shift and down arrow, and now move them to the top. Place them before the ions. So now all of the components are at the top and the ions are in the bottom. So click OK, and save your file, because sometimes the software may stop unexpectedly. So you need to save it, and risk control is every time you make some changes. So now go to the simulation and click on the column. First we will simulate the absorber. So from here you should select this icon, absorber, and install here. Call this absorber, and now click on the material stream, and let's suppose this is the lean solvent, so I will call this lean sol, and just drag it here. So it is entering from the top, and this is the feed gas entering from the bottom. This is the clean gas H2 leaving at the top, and the rich solvent leaving at the bottom. Now specify the feed streams. So in the feed gas, the temperature is 40 degrees C, the pressure is 27 bar, and the mass flow rate is in ton per hour. And this is 100 ton per hour. Mole fraction is given. So it has 0.2% water, so this is 0.002. Carbon dioxide is 18.9%, so 0.189. There is no MDA, no H2S. Hydrogen is 74.5%, so 0.745. And CH4 is 5.8%, so 0.058. Carbon monoxide is 0.4%, so this is 0.004. And 2 is 0.002, which means that is also 0.2%. And now you can see here that this is 1. You should ensure that this is 1. This is the summation of all of the mole fractions. And similarly, this lean solvent, we don't know the flow rate of the lean solvent at the moment, but we want to use an amount which will be enough to recover 95% of the carbon dioxide from the feed. So it is also entering at 40 degrees C and 27 bar. And I will just arbitrarily choose 300 or 400 ton per hour. And the mass fraction has 50% water and 50% MDEA. 50% water and 50% MDEA. Okay, you can click on the next button, so it will guide you to the point that needs your attention. So so now it has taken us to the absorber that where we need to provide some data. We need to specify the absorber. So it has 15 stages. There is no condenser, no reboiler. You know that there is no condenser and no reboiler in the absorption tower. And now click on stream. So the lean solvent is entering at stage number 1 and the feed gas is entering on stage number 15. You need to change this to on stage, because if it is above stage, there will be no separation on stage number 15. Now click on pressure. So the pressure at the top is 26 bar and the stage pressure top is 0.003. Okay, and the efficiency of the stages are mercury efficiency. So select mercury efficiency here. Stage number 1 efficiency is 0.4 and this efficiency of all 15 stages is 40%. So write 15 here and write 0.4 here. So it will actually interpolate between 1 and 15 and it will assign 0.4 to stage number 2, 3, 4, 5 and so on. Okay, now click on reactions. So from stage 1 to 15. Okay, you can see that we have 2 reactions. So this reaction set is for the hydrogen sulfide. We don't have any hydrogen sulfide in our process. So I will just select MDA CO2 and now click on residence time, stage number 1, stage number 15 and select second and spends 5 seconds at each stage. Okay, now go to the convergence. Click on convergence and change this iteration to 200 maximum iteration. Now let's run the simulation. So click on run and so if you click on the stream results, so you will see that and if you click on the mass flows, so you can see that the feed has 75,932 kilogram per hour and the clean gas has 35,000 kilogram per hour CO2. So that means that around 48 or 47% CO2 separated. However, we want to remove 95% carbon dioxide from the feed gas. So let me increase the flow rate of the lean solvent. Let's suppose I will change this to 600, run it. And now if you check the results, stream results, so you can see mass flow now it is dropped to 2100. So which means that now around 70% or 75% is separated, 75% is removed. We want a solvent flow that should remove 95% of the feed carbon dioxide. So for that, we need to utilize the design spec feature of the Aspen Plus. So flow sheeting option, click on design spec, click on new, this one, and here I will define few variables. So click on new, and if carbon dioxide, if CO2, well, if CO2 is this is the carbon dioxide in the feed gas. So the S1 doesn't know that what is this. So we have to tell it that what does FCO2 means. You can choose any name, right, of your choice. So I will tell now the S1 that this is a stream variable. What type of stream variable? The mass flow. Where is the mass flow? And which stream? Feed gas. Which component? Carbon dioxide. So now it knows that what does FCO2 mean. I will now create another variable. Click on new. I will call this HCO2. This is the carbon dioxide that leaving with hydrogen stream. So of course this is a stream variable. Mass flow, which stream? Hydrogen stream, which component? Carbon dioxide. And now we have defined our variables. You can view the variables from here, view variable, or just click on this button so these will be visible. And now click on spec and HCO2 divided by FCO2. So this is the carbon dioxide in the hydrogen stream, and this is the carbon dioxide in the feed stream. So this must be 0.05. That means that if 100 kilogram is entering, so 5 in order to remove 95%, so 5 kilogram must leave. So 5 divided by 100 is equal to 0.05. And you need to provide tolerance. So tolerance is 0.0001 because the software do iteration. So sometimes software doesn't find the exact value. So you need to provide some tolerance. And now click on vary. What we are varying? Stream variable. Which stream? Lean solvent. Which variable? Mass flow rate. In a unit is ton per hour. And the lower limit is let's suppose search the value between 300 and 1000 ton per hour. Now run the simulation, and if you click on the results, so it has found the value. So this is at 31,533 kilogram per hour. This is the value of the lean solvent flow rate, which will remove 95% of the carbon dioxide. So you can check the flow rate, the results here as well. If you click on the input, lean solvent input, it still has 600 ton per hour. However, if you click on the results, and if you want to see this in ton per hour, so in ton per hour, this is 831.53 ton per hour. This should be the flow rate in our for the removal of 95%. So let us check that how much it has removed. So click on the stream results and go to the mass flows. And You can see that this is the flow rate 3794.62 divided by 75932.6. So let me do the calculation in Excel. This divided by this, so this must be 5%. This is almost equal to 5%. 0.05, right? So that means that 95% is removed. Okay, as soon as you get the result, so it is always advised to generate the estimate. So click on under absorber, go to the convergence, and then click on the estimates and click on generate estimates, temperature, liquid, vapor, and click on generate. So these you should always generate this estimate whenever you have a successful when the simulation unsuccessfully, because these estimate will be used in later convergence, because RadFrac these are very hard to converge. So you must have these estimate because later on we are going to change some parameter. If you don't create this estimate, we may not be able to converge. So now this stream is further cooled, heated in a heat exchanger. We call this heat X1, and it is heated up to 110 degrees C. I will call this feed to distillation column. So this is, double click on this, heat it to 110 degrees C, and there is no pressure drop. If I write 0 here, it means that there is no pressure drop. If I write -2, it means that there is 2 bar pressure drop. If I just write 2, that will mean that the outlet pressure is 2 bar. So just write 0 here. So that means that there is no pressure drop, and run the simulation again. So if you want to see the temperature, so just click on temperature here. So you can see the temperature is now 110 degrees C. You can also click on the mass flow rate. So now it is giving you the mass flow rate. So you can see that what does each icon mean. So this is the temperature, this is the mass flow rate. You can also check the molar flow rate and the pressure, etc. Now this stream is fit to the distillation column, the stripper where we will regenerate our solvent. So click on columns, and from here select this distillation column icon, install a distillation column here. I will call this stripper. So is fed here, and I will install one stream here. This is just call this distillate. This is a partial condenser. So that's why I have connected the stream here, and this is the bottom product. So just call this bot. And double click on this column, and it has 30 stages. Condenser is partial vapor, kettle reboiler, vapor liquid, and we are given the boil-off ratio, right? Select boil-off ratio and reflux ratio. And this is on mole basis, molar ratio. So reflux ratio is 0.1, and boil-off ratio is 0.2, as given in the problem. 0.2 boil-off ratio, and reflux ratio is 0.1. And regarding the streams, so it is entering at stage number 10, and the pressure is 2 bar at the top and 0.028. The pressure drop at each stage is 0.02 bar. And now go to the specification. Here enter the efficiencies. So mercury efficiency from stage 2 to stage 29, because the stage number 1 is condenser and stage 30 is the reboil. So this is 0.4 and 0.4, 40%. You also need to add the reaction. So reaction number from stage 1 to stage number 30. Which reaction is taking place? This MDEA CO2. And resistance time, stage number 1 to stage number 1, which is actually the condenser. So it spends 300 seconds here from stage number 2 to stage number 29, 5 seconds, and stage number 30 to stage 30, which is actually the boiler. So it's 300 seconds. Now in the convergence, click on the convergence and change the maximum direction to 200. So just run the simulation. Okay, and here we get the some error. So click OK, and how to converge this? So there is just go back to the stepper, click reactions and remove the reactions, and remove all these. And run this. So now you can see that we have simulated our column and we got the results. So as soon as you get the result, you should generate the estimates. So click on estimates under the stripper, click on the estimate and generate estimate, temperature, liquid flow rate, and liquid and vapor composition, and click on generate. Now again add the reactions. So go to the reaction, stage number 1 to stage number 30, reaction ID, MDSU2, and here write the same from stage number 1 to stage number 1. This is 300 seconds. Stage number 2 to stage number 29, 5 seconds, and stage number 30. This is 300 seconds. Now again run the simulation. Okay, now we have converged the column and we got our results. So controls S and is advised to again generate the estimates. Okay, now I'll go back to the main flow sheet, view main flow sheet, and you can see that this is the top product of the distillation column. It is cooled to 10 degrees C, and then it is flashed to a fresh drum. Similarly, the DA, this is the bottom product. This is cooled to 40 degrees C, and this is also recycled, and they both are mixed here. So I will just install a uh, cooler here. So this is actually heater, so he takes, sorry, cooler, and this is cool to 10 degrees C. Just call this some stream, this one, and double click on it. Outlet temperature is 10 degrees C and there is no pressure drop. Similarly, this bottom okay, and you can run the simulation. And now this is a pass through a flash separator, flash 2. So install flash 2, this flash. So it enters the flash, and in the flash we have this carbon dioxide stream, and this is actually, this is water stream. So it will actually separate the water droplets from the gas. So if you just run the simulation, okay, I think this needs our attention. So if you are unable to find out that why this required input is incomplete, so just click on next, and it will take you to the point that needs your attention. Don't forget to press Control S whenever you have some changes. So it is operating at 10 degrees C and there is no pressure drop, right? Just run it and check the results, stream results of the flash. So you can see that you click on the mole frictions. You can see that the water stream, it has 99% water, and in the carbon dioxide stream, it has, okay, where is carbon dioxide? Yeah, this, you can see that this has 94% carbon dioxide. So we are going to recycle this stream. No, not this stream, sorry. We will recycle this stream, right? This one, this stream. Because this is water, this will be again recycled to the absorber. Similarly, this, okay, let me just install a mixer here. Mixer, and if I click R, so you can flip this by clicking R. You can actually rotate this by clicking R, and just double click on the arrow, and so here you can see that I have recycled this into this mixer. So the mixer also have an outlet stream. So just call this REC. Okay, ensure that you join it here, and this stream, if I double click on this stream, it contains only MDEA and H2O. So mole fraction, so you can see that it has 86% H2O and 13% MDEA. And if you click on the mass fraction, so you can see that it's 50% H2O and 50% MDEA almost. So this is this one is also cool to cooler 2. Sorry, I don't install it. Install the heater and call this cooler 2. Okay, you can rotate it. Okay, just click on R, so rotate this, and if I double click on this arrow, so you can join it here, and also add here. So this is, just call this series 1, and you can double click on it and feed it here. So run this simulation again. Okay, there is something that needs our attention, so just click on next. So this is the cooler 2, yeah. So we want to cool this to 40 degrees C, and there is 0 bar. Okay, just now run it, and here you can see that how much we have recovered, how much solvent we have recovered. So this is if I click on ton per hour, so this is 832.56 ton per hour is recovered, while our fresh solvent was, if you check that result, so this is our fresh solvent. So this is in ton per hour, 831.2. It is actually the flow rate of the H2 and MDEA. This is important, right? And this is the REC stream, I think, yeah. So you can see that we change this to ton per hour, tons per hour. So you can see that R just changes to kilogram per hour, so that the difference is visible. Kilogram per hour. Sorry, kilogram per hour. So you can see that we have 41,415 water in the lean solvent, but it has reduced to 414201. And similarly, MD is also reduced. The reason is because some of the, if I click on the H2 stream, so you can see that this much water is lost with the H2 stream, and this much MDA is lost with the H2 stream, which is leaving the absorber. And if I click on the carbon dioxide stream, so you can see that this much water is lost with the carbon dioxide stream. So that's why in the recycle stream we have less water as compared to the lean solvent, and same for the MDA. So now what we are going to do, which we'll do in the second part, that we will use the makeup solvent, this makeup solvent, right? Makeup solvent, which is the makeup solvent which is lost with the carbon dioxide and H2. So we will do calculation for that, and then we will recycle our regenerated solvent to the absorber. See you in the next video.